For today's topic, we're going to discuss about empirical formulas. And first, let me introduce you to this concept. And we've been talking about. This is a very busy slide, and let me guide you through it. But you've seen that before in a previous podcast regarding the percent composition, as we talked about. Call up the pen, and when we mention the calcium carbonate, because calcium is +2, carbonate is CO3 2-, we have this particular formula CaCO3. Notice the subscript and the convention of putting a cation first and the anion second, the carbonate being a polyatomic ion. And now we're starting listing it out because we look at the formula. We know calcium has one, in any 1 mole of this compound, we will have 1 mole of calcium, 1 mole of carbon, 3 moles of oxygen. For each mole of those elements, and that's equivalent to the atomic mass in grams for this compound, for this element. This is what the concept about the molar mass. And by looking at the periodic table, one can quickly identify molar mass for calcium will be 40. That's the average atomic mass for calcium element. 12 grams will be the molar mass for carbon. 16 grams will be the molar mass for oxygen. And we essentially have to add all of them together, since there's only one calcium in the calcium carbonate. So you have 1 multiplied by 40, got 40 grams. 1 multiplied by 12 grams. 16 minus 3, because since you get the 3 moles of oxygen, you get 46 grams. That is the 48 grams contribution to the mass from the oxygen atoms in the molecule. In this molecule, or in the ionic compound case, we call it formula units. So when you have this, is about added all of them up, is about 100 grams per mole. That means 1 mole of calcium carbonate is equivalent or equal to 100 grams of calcium carbonate. And from that, we can actually quickly figure out what we call the percent composition. Percent composition simply is the percent by mass for one particular element. In this particular case, we're talking about is 40% of the mass is actually coming from the calcium atoms, and 12% from the carbon, 48% is from the oxygen. So those are the well defined in the previous vocast, and today we're going to put a little bit twist on that. And also, if we say calcium carbonate, let me change the color. Let me change the color of the pen. And on one hand, you will know calcium carbonate is this particular formula. You have calcium. You have 1 mole of the calcium carbonate. You have 1 mole of calcium carbonate, 1 mole of calcium, and 1 mole of carbon, and 3 moles of oxygen. This readily can derive from this formula. On the other hand, we will have you can analyze this compound. It will break down into calcium and carbon and oxygen, and it can be readily analyzed to be 40% by mass, and that would be 12% by mass, and the oxygen the oxygen is 48% by mass. It's 48% by mass. Let's put it into this box, and let's put it into a separate box for those. And hypothetically, if only this box is known, or sometimes referred to as actually those information can be readily obtained by chemical analysis of the compound. Literally can take the compound, start breaking them down, and analyze the percent composition for each element in this compound. If this is the information we know, can it be done? So we can actually, from this known information, actually derive the relationship above, and essentially the ultimate goal is actually derive a certain kind of a formula to represent the compound. And actually there's a way. Remember, this is called percent. This is called percent composition. So we can readily break them up into grams if we can follow the following process. Let me write it down in a clear visual way. So then I'm going to write steps on this side. So, and I'm going to write what is actually happening regarding this. If we have known this information, calcium is 40% by mass, carbon is 12% by mass, oxygen is 48% by mass. Okay, so I like to work in a tabulated form, very organized, very visual. Step number 1, you assume 100 grams, 100.0 grams to consider the suffix grams of the compound. So you can convert percentages into grams. Okay, in this case, you take 100 grams of compound, so by the percent composition definition, you should have 40 grams. You should have 40 grams of calcium, 12 grams of carbon, and 48 grams of oxygen, because it's this one just times 100. Okay, and now you can see molar mass for each element, and you can readily obtain that from the periodic table. That would be 40 grams. That would be 40 grams for calcium, 20 grams for carbon, and 16 grams per mole for oxygen. Okay, so this is grams per mole, this is grams per mole, this is grams per mole. Okay, so that would be second step. Take the molar mass of elements, convert mass into moles. Okay, in this case, you have to take 40 grams divided by 40 grams per mole. If you're a little bit confused, use the monkey bar, set it up, and trust me, the 40 grams will be appearing on the denominator. So it's actually, so those are for mole of each element. Okay, so this is step 1. That will be step 2. And 40 divided by 40 will be 1.0 mole, and this one will 12 divided by 12, 1.0 mole, and this one will be 3.0 mole. Okay, so number 3, take the mole ratio of elements get to the simplest. So if you want to take that, that will be step 3. you still have calcium, carbon, oxygen since I'm running out of space. This is just direct translation from the right side. And number 3, you're going to take the ratio is becoming 1, 1, and 3. And from here, we can now write the empirical formula for the compound. In this case, we know is calcium, we know it has 1 carbon, will have 1 oxygen, we have 3. We have 3. Very, very important process. And take your time to understand this. So essentially, you take the mass by the percentage mass, convert it into mass in grams, convert the grams into mole of each element, and take the mole ratio of each element. That would be the number ratio for each element in the formula. If you get the simplest form, in this case it happened to be the simplest form of 113, then you can actually get to this what we termed empirical formula. Let's define this term. So what we refer to as empirical formula of a chemical compound is the simplest and very, very important. It's the simplest positive integer ratio of atoms of each element present in the compound. In the past, in the previous example we used, and that would be calcium carbonate, you did have the ratio between calcium, between carbon, between oxygen is 1, 1, 3. Hence, empirical formula CaCO3. Okay, so let's take a look at one example, guide you through all the steps, and put it into a very visual and easy to understand, and so one can actually consistently carry out the process. Read the question. A compound was found to contain sodium, sulfur, and oxygen. Percent compositions were found to be 32.4%, 22.5%, and 45.1% respectively. And the question is to find empirical formula. So first, got to understand the question. These percentages are the mass percent of sodium, sulfur, and oxygen. So if we want to write it down, so we're going to get sodium and sulfur and oxygen. Sodium, sulfur, and oxygen. So let's see. First, we can see it's 32.4%. It's sodium, 22.5%, sulfur, 45.1%, oxygen. Okay, so you take 100 grams of the compound, so this one immediately convert to 32.4 grams, 22.5 grams, 45.1 grams of each element. Then check the periodic table, take the molar mass of sodium will be 23 grams per mole, and they will be 32 grams per mole and 16 grams per mole. As you can see, these numbers are not exactly matching the atomic mass number on the periodic table, but they are very, very close, because a lot of those have decimal points. You can actually run it up without introducing too much error into the subsequent calculations. So you now take that, and obviously you can find the mole for each element present in the compound by take the mass divided by the molar mass. Or if you're not feeling comfortable with the proportionality, you can use the dimensional analysis. When you start with the grams of the element, you want to get to mole of the element. That gram of the element has come down to the denominator, and then now you have to keep that up and down part of the fraction. It has to be equal to 1. Remember the conversion factor concept. So 1 mole of the element has to be equal to the molar mass in grams of that element, and hence you can have, so this is mole of each element. Okay, so then just a little bit of reminder, step 1, this is now we have step 2, and in this case you have 1.409 moles of sodium, 0.703 moles of sulfur, and 2.819 moles of oxygen. So we're going to still proceed. Number 3, that will be the mole ratio. Okay, so now this one will be 1.409. My advice is when you calculate empirical formulas, put the last suffix to the thousands, which means the third digit after the decimal point. So this one is 1.409, and next one will be 7.03 and 2.819. But remember, for the empirical formula, we're looking for the simplest whole positive integer ratios, but those are not integers. And let me show you some further process before we can actually come back. And if you can say sodium, it's a ratio between sulfur and oxygen. We're talking about mole ratio. Okay, so in this case we will have 1.409 over 0.703 over 2.819. Very interesting fact to recall for your mathematics. If it's ratio, is actually you can take the values for each, and you can divide it by any non-zero numbers. So the ratio, the relative ratio between those elements do not change. In this case, this is one of the things of the tricks you do. You take the mole number with the lowest value, smallest value, and you simply divide each one of them by it. And now you should have, this is about 2, and absolute divided by 1 divided by itself, and this is 4. This is 4. Now we're reaching the simplest integer, the simplest positive integer ratios. So it's 2, 1, 4. So the empirical formula for this particular compound would be Na2SO4. That will be the answer. That will be the answer. That will be the empirical formula for this particular, or we call it inorganic compound. Inorganic compound. And let's pause here for a minute or two, and a lot of information to digest. I would advise you to really go slow on this, trying to understand. Before we do that, let's complete that. So this one will be 2, 1, and 4, because what we did is take the smallest number, divide each one by it. Okay, and if you feel comfortable, you actually master this. Let's do the following 3 problems, and as you know, all in my podcast, the answer is right on the next slide, but I would strongly advise you not to look at the answer first, but work on the problem, use the process I outlined in this podcast. And if you get all the answers, then you are completing this module, and move on to the next one. Okay, and thank you very much for your attention, and that wraps up this particular broadcast.